Differentiability. Let us recall the definition of derivative of a real function. Suppose f is a real function and c is a point in its domain. The derivative of f at c is defined by limit h approaches 0, f of c plus h minus f of c divided by h, provided these limits exist. Derivative of f at c is denoted by f dash of c or d by dx of f of x at c. The function defined by f dash of x is equal to limit h approaches 0, f of x plus h minus f of x divided by h whenever the limit exists is defined to be the derivative of f. The derivative of f is denoted by f dash of x or d by dx of f of x, or if y is equal to f of x by dy by dx or y dash. The process of finding derivative of a function is called differentiation. Algebra of derivatives. Let u and v be two functions. Then differentiation of u plus or minus v is equal to differentiation of u plus or minus differentiation of v. Differentiation of product of u into v is equal to differentiation of u multiplied by v plus u multiplied by differentiation of v. Differentiation of u divided by v is equal to differentiation of u multiplied by v minus differentiation of v multiplied by u divided by v square. If a function f is differentiable at a point c, then it is also continuous at that point. Let us prove this theorem. Since f is differentiable at c, we have limit x approaches c, f of x minus f of c by x minus c is equal to f dash of c. Now, f of x minus f of c can be written as f of x minus f of c divided by x minus c into x minus c, provided x is not equal to c. Applying limit x approaches c on both sides, we get limit x approaching c f of x minus f of c is equal to limit x approaches c f of x minus f of c by x minus c into x minus c. By the algebra of limits, we can write limit x approaching c f of x minus f of c as limit x approaches c f of x minus limit x approaching c f of c. Similarly, limit x approaching c f of x minus f of c by x minus c into x minus c can be written as limit x approaching c f of x minus f of c by x minus c into limit x approaching c x minus c. Limit x approaching c x minus c is equal to 0 and limit x approaching c f of x minus f of c by x minus c is nothing but f dash of c. Substituting the corresponding values, we get limit x turns to c f of x minus limit x turns to c f of c is equal to f dash of c into 0, which is equal to 0. Therefore, limit x turns to c f of x is equal to f of c, which implies the function f is continuous at x is equal to c. So we can say if a function f is differentiable at a point c, then it is also continuous at that point. Now let us see whether the converse of this theorem exists or not. That is, whether every differentiable function is continuous or not. Let us take an example of mod function. Let f of x is equals to modulus of x. We know that modulus of x is a continuous function. Now, the left hand limit of this function is limit h approaching 0 minus of f of 0 plus h minus f of 0 by h, which is equal to negative of h by h, which is equal to minus 1. And the right hand limit of the given function is limit h approaching 0 plus of f of 0 plus h minus f of 0 by h, which is equal to h divided by h is equal to 1. Since the left and right limits at 0 are not equal, limit h approaching 0 of f of 0 plus h minus f of 0 by h does not exist, and therefore the function f is not differentiable at 0. So, every differentiable function is not continuous. We can say that all the differentiable functions are continuous, but all the continuous functions are not differentiable.